When your application scales beyond a single instance, standard WebSocket connections break. Load balancers distribute traffic randomly, destroying the required persistent connection state. If user A connects to server 1 and user B connects to server 2, a message intended for user B originating from server 1 never arrives. Sticky sessions are a fragile workaround, failing under high churn or complex deployment environments like Kubernetes. The fundamental requirement is a shared message backplane, accessible by all application servers. This backplane must decouple the message producer from the consumer, allowing any server to broadcast data regardless of which server holds the client connection. We implement this using Redis PubSub, transforming the architecture from point-to-point to a robust distributed fan-out system. Redis PubSub provides the necessary message bus abstraction. Each application server hosting WebSocket connections acts as a subscriber to specific Redis channels. When an event occurs, the originating service, which might be a separate microservice or the same application server, acts as the publisher. The publisher executes the publish command, specifying the target channel and the payload. Redis then immediately broadcasts this payload to every currently connected subscriber listening on that channel. This ensures that if 10 application servers are running, all 10 receive the message simultaneously. The key benefit is zero knowledge transfer between the publisher and the subscribers regarding the number or location of the connected WebSocket clients. On application startup, the WebSocket server must establish two distinct connections to the Redis instance. The first connection handles standard data operations, like storing session information. The second connection is dedicated solely to the PubSub subscription mechanism. This separation is critical because a connection actively listening for subscriptions blocks all other commands. Using a library like io-redis in Node.js, we instantiate a dedicated subscriber client. We then execute the subscribe command, targeting a global channel, for example, global:broadcast. The server registers a callback function that triggers upon receiving a message on this channel, initiating the fan-out process to its locally connected clients. A service needing to send a real-time update, perhaps a payment confirmation service, constructs a standardized message payload. This payload must include the actual data and metadata specifying the target audience, such as a user identifier or a room identifier. We recommend serializing the payload using JSON for interoperability across different service languages. The service then executes the publish command against the Redis instance. For instance, publish user:updates, user ID:42, event: order complete, unquote. The channel name itself, user:updates, dictates the scope of the broadcast. This design ensures the publishing service remains lightweight, offloading the heavy lifting of distribution entirely to Redis and the subscribing WebSocket servers. When the dedicated Redis subscriber client receives the message payload, the registered callback function executes. This function must first deserialize the JSON payload. Next, the server iterates through its local map of active WebSocket connections. If the payload metadata indicates a specific target, the server checks if that target, identified by a session ID or user ID, is present in its local connection map. If a match is found, the server calls the WebSocket send method directly on that specific client object. If the message is a global broadcast, the server iterates through all local connections, sending the message to every client it manages. This local fan-out is the final step in delivering the message across the distributed system.
Effective scaling requires mapping user sessions to specific, targeted channels. When a user authenticates, the WebSocket server must associate the user identifier with the local connection object. Simultaneously, the server executes the psubscribe command, subscribing to pattern-matched channels, such as user:42 private or room:101 *. This allows for granular message targeting. When a client disconnects, the server must immediately execute the punsubscribe command for all specific channels associated with that session to prevent resource leaks and unnecessary message processing. Maintaining this dynamic subscription state ensures that messages are only processed by the servers that actually hold the relevant client connections. The Redis backplane fundamentally eliminates the requirement for sticky sessions at the load balancer level. Since every application server subscribes to the necessary channels, any server can handle any client connection. The load balancer can employ simple round-robin or least connection algorithms, distributing traffic evenly. If a client connects to server A and the message originates from server B publishes to Redis, and server A receives the message via subscription, delivering it locally. This architecture allows for seamless scaling up or down of application server instances with complex session affinity configurations, significantly improving deployment flexibility and resilience against server failure. The primary failure point is the Redis connection itself. If the WebSocket server loses connection to Redis, it stops receiving real-time updates. Implement robust reconnection logic with exponential backoff for the dedicated subscriber client. Crucially, Redis PubSub offers no message persistence or guaranteed delivery upon subscriber failure. If a server goes offline and misses messages, those messages are lost. For critical data requiring guaranteed delivery, PubSub must be augmented with a persistent queue mechanism, such as Redis streams or a dedicated message queue like RabbitMQ, where the WebSocket server polls for missed messages upon reconnection. Latency in this system is dominated by three factors: network transit time to Redis, Redis processing time, and serialization or deserialization overhead. Minimize payload size by transmitting only essential data. Use efficient serialization formats. While JSON is standard, consider binary formats like MessagePack for high-throughput scenarios. Ensure the Redis instance is dedicated and not overloaded with heavy database operations. Monitor the Redis command statistics, specifically the number of publish operations, to identify bottlenecks. For extreme scale, consider using Redis cluster, although PubSub operations are generally handled by a single shard, requiring careful channel design to distribute load if necessary. We have successfully decoupled the message production from the client connection state. By leveraging Redis PubSub as the central nervous system, we transformed a fragile single-server WebSocket setup into a horizontally scalable multi-instance architecture. This design ensures that every application server acts as a stateless conduit, relying entirely on the Redis backplane for message coordination. This approach is essential for modern microservice environments requiring high availability and real-time data synchronization across hundreds or thousands of concurrent users.